So today we will start with the forward end and aft end construction. To some extent we have talked about it in some of our previous lectures. I mean, as you can see the name, forward end construction, right? In short, it is written like this, end, or also it is written as fore end. That means the forward end of the hull, this part only. What is the great difference between these two hulls? Just only this part I have drawn in here. This here you have the bow. This is what is referred to as bow of the section. Here you have a bow straight going up with at an angle, at a particular angle, right? So this angle could be from 90 degree to some less than 90 degree, right? Generally it is not made 90 degree. Generally a rake is given, such inclination is given, right? Those details, why and how much effect, those things you will learn in some other course. But well, for general cases, either the forward part, the bow of the vessel, or the forward part looks like this, or the other alternative is here. Here you can see some extra, as if some extra construction has been provided there. Instead of having the bow going like, as we have said, that conventionally, or well, going like this through the dotted line I have shown, as if some appendage has been added. This is what is referred to as, you have heard about it? You know what it is called by chance? Well, it looks like a bulb, as if some kind of a bulb as if has been put there. The cross section of this bulb, right, could be, if I see the cross section, right, the cross section could be, well, let me, some of them, it can have a section like this, it can have a section like this, or even it can have a section like this. That means it can be either right from a circular section to some oval kind of section to various different means mostly these type of sections. It's a inverted sort of a trapezium kind of a thing, right? It's it can be as if a rounded off rectangular section, a circular section. So different kinds this thing could be. It is referred to as bulbous bow. This particular appendage, as I mean the way I have shown here through the dotted line, as if this was the original hull and then this bulbous bow has been attached. But in reality, of course, this part of the original hull is not there. Straightway the bottom shell continues, right, and it takes some such shape as a bulbous bow. There is a definite purpose why this is put. Well, I mean, you will learn much more about it. In one sentence, it can be said like this, that providing a bulbous bow, it reduces the resistance of the vessel. Resistance means resistance of motion. I mean, when the vessel is plying through water, the water medium offers resistance to its movement, right? So our objective is always to how to reduce that resistance to a minimum, because then I can have a very efficient propulsion, right? Our fuel consumption will be less. So this is one of the way of reducing that resistance by providing a bulbous bow. how that happens? Well, that we will learn later. So, my forward end, either it may look like this case number 1, or it may look like this, the case number 2, wherein you have the bulbous bow in the case number 2, then the bulbous bow can have different kinds of sections. That is as far as the external view is concerned, and that too which is visible in the profile section. By profile section, I mean the section through the longitudinal central line, a section through the longitudinal central line, or the central line along the length of the vessel. If I take a section, I get the profile. It will look like this. Now, if I take a section here, that means transverse sections, right, transverse sections, then also you may have the forward sections like this. Or what is the difference between these two? These are the sections about this. Suppose this is my YY, right? About this YY, the sections are taken. Obviously, of two different forms. So, what we can see here is that this particular is having a much larger flare. Both are, suppose they are having the water line here, right. In this we see that it is having a much more flare. This is what is referred to as flare. The side shell is flaring out, right, side shell is flaring out. So, in this what happens, you can see the water plane at the load water line is much narrower in this case compared to this. So, well, for a different hull form, for a different block coefficient, all these things you have heard about, some of those form coefficients, right. So, if the form coefficient, if the block coefficient is less, then it will tend to this type of a section, this type of a section, which is, suppose this is number 2, this is number 1. With a higher block coefficient, it will tend to be like this. But in both the cases, I am having more or less the same deck area. Let us assume that these two sections are taken more or less at the same location of two near identical vessel, right. Only thing, in one vessel the block coefficient is of the order of say 0.8, in another vessel the block coefficient of the order of 0.6. So, 0.8 would be somewhat like this, 0.6 would be somewhat like this. So, you provide a much bigger flare, so that you achieve the required deck area, right. Less flare, much flare is not needed, because you do not unnecessarily widen the deck, okay. But by doing this, what is happening? Okay. So, these are actually based on the requirement of block coefficient and other aspects. Now, once the lines and how the hull form would be has been decided, then one goes for the scantling calculations. Now, scantling calculations and followed by stiffening arrangement, which is the aspect we are looking into. So, as we go for stiffening arrangement, then we see that a somewhat little extra care is given to these forward end constructions. Forward end construction, though we have talked about that, if is the primary strength considerations are essentially because of the longitudinal bending. Because of the longitudinal bending, the longitudinal bending moment is somewhat like this, right. So, we see that around the mid length of the vessel, I have maximum bending moment, right. This is my bending moment curve. So, as we go forward or aft, the bending moment is 0. So, the load coming due to the bending moment or the stresses generating due to bending moment in the forward end is gradually going down, it is lower. So, in the process what happens as we move from the center to the forward, we will see that there is a gradual reduction in plate thickness, gradual reduction in the scantlings of the stiffeners, right. But again when we go beyond a certain point and go further forward, then again we see rise in the scantlings. That means there it is no more the case of the stresses due to bending moment, but it is the local loading which comes into play, right. Local loading takes over. So, in these two forms, as you can see, if both the vessels are plying and imagine it meets a somewhat rough weather and the vessel starts heaving. Heaving means it goes vertically up and down. Heaving is this motion, goes vertically up and down, or for some reason if it slams is as if about some horizontal axis it is oscillating, that is slamming, right. So, either heaving or slamming, in both the cases this type of form is going to experience much higher loading in this area, because this surface is bigger, it will go on hitting the water surface, whereas in this the load will be less somewhat. In any case, both will be subjected to that load due to the slamming of the water surface, that means the local loading, primarily the local loading.
So, which will have greater slamming?
Greater slamming will have the one which is having bigger flare, the one which is having bigger flare. From the very simple, from this figure you can see that here the water hitting this effect will be less, but here the effect of this surface hitting the water effect will be much more. That means, if these are my load vectors, these will be bigger, right, because it is a more projected, more area which will go and hit the water surface, right. So, in any case, what we like to highlight is that means the forward end of a ship is subjected to primarily local loads, of various kinds. One is due to the ship motions of heave or slamming, right, that is the underwater hull will get affected because of that. Another is, as we have said, that the deck plating, right. The deck plating means you have the, suppose I am just drawing the forward part of the ship, this is your water surface. Now, in a bad weather, right, there can be, the waves may become too high and come and hit the deck, right. So, you need additional strengthening at the deck to this water coming and falling on the deck, right, they are referred to as green waters. The terminology is shipping in green water, that is how it is referred to, shipping in green water. I mean, it does not have anything to do with the color of the water, it is just the way it is said, right, shipping in green waters. So, anyway, this can be really huge, right. There are instances that this water coming and hitting here and made a hole in the deck, because such a huge mass of water comes and falls, that force breaks open the deck. So, that is how we see that the forward end has to be additionally stiffened, not only the bottom shell part of it, because bottom shell is subjected to your loading due to the slamming action of the or heaving action of the vessel, and this is because of the shipping in of green waters, right. It needs extra loading, though the stresses due to bending moment is near 0. So, that is how we see it is primarily the local load. And second aspect is, as you know, that this particular bulkhead, this is the forwardmost bulkhead it is referred to as, I have told this. Do you recall? Forward collision bulkhead. Forward collision bulkhead, or also referred to as fore peak bulkhead. Right, fore peak bulkhead. This is fore end, forward end, or fore peak. Also, that term is also used. Fore peak. This is a fore peak bulkhead. Right. What is the very logic of this? Why this name forward collision bulkhead? Yeah. So, idea is, in the event of some situation where the ship may hit head on, then this part should be able to absorb the entire impact load. So, to do that, you can well imagine the momentum of the vessel by virtue of its size. So, that impact, if it has to take care of, it has to be of heavy construction. Right. So, that is how fore end construction is, well, is taken separately. Like we will later see that the midship section, midship construction is taken separately. Similarly, fore end construction is also taken separately. So, what are the salient features of this forward end construction? One of the salient feature is, if we in ship construction, when we go about the primary, you can say the primary frame of reference in ship construction is the so called frame spacing, right. Some particular, so because you see, I mean, whenever you want to suppose construct something, fabricate something, you should have a something, what one may say, a starting point. Suppose I say then that the length of the pane is, say, 10 centimeter. What does that mean? That means from some point to some point, 10 centimeter. Or if I say add a component at the 10th centimeter position. So, well, if I say add a perpendicular component at 5 centimeter position of the pane. Now, whether this or this, because both are 5 centimeter, this is 5 centimeter from here, this is 5 centimeter from here. So, I have to give a frame of reference. I have to say from the forward end, I mean after, suppose this is my forward end, if I refer in the ship terms, after 5 centimeter after forward end. So, it comes here, or I say 5 centimeter forward of, sorry, it was what I said, 5 centimeter after forward end, right. Here I will say 5 centimeter forward of aft end. So, that aft end, forward end, these are the frame of references, well defined frame of references. We should have that. Not only that, this very simple example, as I have said, this entire hull, as we have seen, is composed of stiffened panels. That means individual flat or curved panels, and then subsequent units, blocks, all those things will be constructed. One will be joined to the other. So, how do we know that which one, where, and what distance, all that? So, the primary reference is the frame spacing. That gives me the reference of the location of my stiffeners, as well as the entire definition of the vessel comes from this frame spacing. Now, it should start from a 0th frame. So, that is fixed. I mean, whichever way you want, wherever you want to fix that, fix it. Generally, by convention, it is fixed at this point, which coincides with the, what is it? What is this line? After perpendicular. Generally it is done that way, that this is my, well, let me write here, is after perpendicular. So, this frame here becomes what? -1, simple. minus 1, this is 1, 2 and so on, right. And the outer perpendicular is the location where you have the center line of the rudder stock. There is a rudder for maneuvering the axis, vertical axis of that shaft of the rudder, which is called rudder stock. Anyway, so I coincide my 0th frame location with the outer perpendicular. Then I have 1, 2, 3, etc. So that gives me then I can define any plate anywhere, right. Suppose a patch of plate here, I can define that. I can say that it is between frame 35 to frame 60, right, or it is 100 millimeter. I mean the frame 35 is 100 millimeter forward of one edge. From one edge 100 millimeter, draw a line, that is frame 35, and say the frame 60 is the location 50 millimeter before the other edge. In any case, so this way the whole thing can be defined. Well, so frame spacing is, it plays an important role as far as giving the references. Second important role is spacing of stiffener. So I can have it small, I can have it big. Spacing can be 500 millimeter, spacing can be 1000 millimeter. So what spacing I will take, that will again depend on your depending on your structural design, what you are carrying out. If you choose 500, it will give you something. If you choose 600, something else, and so on and so forth. So how do we choose this frame spacing? On what basis should be there to decide upon the frame spacing? I mean, this is in general, this has nothing to do with forward end or aft end. So it will be worthwhile to look into this aspect also. Say a panel is there, well, two identical panels. Sorry, I mean one looks smaller, another is bigger, but let us assume both are of the identical overall dimension, 5 meter by 6 meter, whatever, identical overall dimension. And in one case, I have frame stiffeners, say 500 millimeter apart. I have stiffened it, let us assume in this fashion. Let us say transverse stiffening. In another case, I have stiffened it 1000 millimeter apart. So straight away the effect would be, in one case there will be less number of stiffeners, in another case more number of stiffeners. What will be the other differences? Because my final objective is that both the panels is to sustain the whatever design load. That means they should be structurally sound under the service conditions. So what I will expect, let us draw a little exaggerated view of these sections, a section through this, right. Exaggerated view means, let me put by double lines showing the thickness, and by single line the stiffener scantlings. Say it is going like this. What would be the case in this? What would be the difference? Definitely, it will be spaced far away. Scantlings will be higher. Simply, scantlings ought to be higher, isn't it? Because here, whatever suppose loading I am considering in this direction or whatever, the section modulus it is giving because more number of longitudinal, here it is less number of longitudinal, but the section modulus requirement has to be same, isn't it? Suppose both are being subjected to similar bending moment. If that is so, then I have, because what finally I have to satisfy is the stress whatever is coming, right, it should be less than equal to your working stress. the same bending moment. So, Z will either will be higher or lower. That means, here physically it would be something like this. That means, the plate thickness will be expected more, right. Your scantling of the stiffness will be also quite high, right, like that it will go. So, what is the ultimate difference between these two? So, which one to choose? Now, tell me. Here I have provided frame spacing 500 millimeter, and here I have provided frame spacing 1000 millimeter. Which one to choose, or choose something else altogether? 500. No, what should be the criteria? There has to be some criteria. Strength by weight ratio. Simple. The criteria should be strength by weight. It has to be maximized. Right? Now, I cannot say offhand whether the option 1 gave me a higher this, or option 2 gave me a higher of this. So, in fact, for doing it more systematically, one should do for various frame spacings, right, and then plot a curve and see where you are getting the minimum. Say various frame spacings, you have 500, 600, 700, 800, 900 and 1000 suppose, right. And here you have the, instead of going by strength to weight ratio, I can straight away calculate only the weight. I have to minimize the weight, because strength all are giving same, near same, because that criteria we have satisfied through this. So, straight away only the weight. So, it is expected that the curve would be, how the curve would be? Curve would be, well, possibly something like this. That means, well, I do not know, I have not done this exercise, but what I have drawn is that shows that both, whether I put 500 for a given case, of course, I mean it is not a universal truth, for a given case, for a given loading condition, for a given plate material, right, that providing frame spacing as low as 500 and providing as high as 1000, both are giving higher weight of the structure. So, somewhere in the middle is my better value. That could be, say, I do not know, could be 800, right. So, well, the logical way would have been this, that you find out the frame spacing wherein you have the minimum weight of the structure for the same strength, right. So, once that is done, but in reality, in practice, what is done is you take help of the standard rules laid out in the classification society, right. There some standard formulae are given through which it is easily done, right. So, from there you choose what is the, but the basic philosophy is this in the behind, that you choose what should be the frame spacing. So, once the frame spacing is done, what does that mean? That means the spacing between these lines I have drawn, they are basically say 800 millimeter, right. That means at every 800 millimeter there will be a stiffener, or every multiple of 800 there will be a stiffener. So, if the, say, the side shell is transversely stiffened, I will have every frame position a transverse frame, right. The deck, if it is longitudinally stiffened, the frame locations by the frame position, you are dividing the ship in, I mean there is imaginary division, right, and the deck is, if it is in this plane. So, there also we take recourse to the this frame spacing, because deck would be like this, right. say I have my after peak bulkhead here and these are my longitudinals. So, spacing between the longitudinals also will be equal to that frame spacing. And if you are providing a centerline, if you are providing a girder here, suppose I have the hatch opening here, then this particular longitudinal is replaced by a hatch side girder. So, the hatch opening I will not make arbitrarily, I will make in such a fashion that the hatch side girder also comes in some multiple of frame position. Why? Because then it becomes easy for me to keep track of where what is there, the stiffeners, because the deck will be fabricated in multiple number of pieces, several, it could be few hundreds. So, all those 100 pieces when you want to put them together, everything should match, not only the plate, the stiffener. Suppose I have a, suppose there is a joint here, means what? All these longitudinals should match, you know. So, anyway, so that is what is a function of frame spacing. I mean, that is how the frame spacing concept is used. And from the strength point of view, so what we see, we will find, suppose as I have said, say for this particular vessel, I take a frame spacing of 800 millimeter. So, we will find the frame spacing going like this. Here, you will have 800, say this is my aft peak bulkhead. So, generally you will find the entire this region is 800. Then from the fore peak bulkhead forward, it is reduced, the frame spacing is reduced to how much? 610 millimeter, irrespective of whatever the frame spacing was here. Had it been 500, then it remains 500, but if it is 700, it becomes 610, it is 900, it becomes 610. That 10 thing has come because it is converted from some feet, you know, and that is how that 10 has remained. But the point is, that means you are not permitted to have a frame spacing greater than 600 millimeter forward of fore peak bulkhead. What does that mean? That means I am putting closely spaced stiffeners, and closely spaced stiffeners, one implication is that it will become heavier, let it be, but stronger also, additionally stronger rather. There I am not only looking into this, this is essentially due to bending, isn't it, because you have the bending moment. But here I am looking for the local loads, right. So, thereby I make the spacing lesser, and instead of straight jumping from 800 to 600, there is generally a some distance before it is reduced to say 700 and then to 600. How much before? These are all laid out. It is prescribed. I mean, the advantage of our doing all this job is things are generally prescribed. You will have to read, understand, properly interpret and apply to your requirement. Right. So, this zone is called pounding area. I mean, from where it is becoming 700, pounding, this area is called pounding, means as if it is pounding on the water surface, the slamming, right. Thereby you have lesser. So, that is one of the aspect, that forward of fore peak bulkhead, your frame spacing has to be reduced to 610 maximum. It can be less than that, but cannot be more than that.
So, then the matching of those transfers will not be.
No, transverses, there is no problem in the transverse sections, right. So, yes, what happens in that case, that does not mean this 600, the frame spacing I have reduced here. So, all the transverse members come to 610 millimeter spacing, and the forward members, the longitudinal members, what is happening is, it is like this. If I see the deck plan, say the deck plan is like this. Obviously, we are drawing just the half of it, right? Let us assume my forward peak bulkhead is somewhere here, right? After peak bulkhead is somewhere here, and let us draw only one or two longitudinals, just because no point drawing all. And why I am drawing longitudinal, not transverses, because I said that it is a wise thing to do is to provide longitudinal stiffening arrangement, because that gives you better buckling strength. If the same deck I would have had provided transverse stiffening arrangement, then the weight of the deck would have been more, or strength to weight ratio of the deck would have been poorer, in one sense poorer, lesser, had this deck been stiffened transversely. Why? Because by providing transverse stiffening, I will have to take care of the longitudinal bending, and that longitudinal bending may cause buckling. So, to provide for required buckling strength, I will have to provide for additional scantlings, higher scantlings, additional longitudinal members probably. You have the transverses, higher longitudinal members. So, eventually the structure would have been inferior from that point of view, strength to weight ratio point of view. So, well, in that case, we will rather prefer a longitudinal stiffening arrangement like this. So, you see these stiffeners as I am drawing, they are going very nicely. Only thing, the last one I have stopped there. The whole idea is, if I go further, it hits the shell. As I have said, you cannot terminate anywhere in the shell, just the end hanging. It has to be properly terminated in a transverse member. So, there is one of my transverse member, which is referred to as deck transverse, right? Deck transverse we will see while doing the midship sections. I mean, I have shown you some of it. The deck transverse, one of the version of deck transverse is the hatch end beam. The same deck transverse, when comes at the hatch end, we call it hatch end beam, right? So, this deck transverse will be, well, widely spaced. For a longitudinal framing system, my transverses, the transverse member will be spaced 3 to 4 times the frame spacing. 3 to 4 times the frame spacing. Anyway, so it is terminated here at that. The other two are terminated in the fore peak bulkhead. Then what happens if I go still forward? So, still forward if I go, then it becomes very difficult, because the shape is closing sharply, right? Right. Not only it is closing sharply, and also not only you extend the this longitudinal, but wherever it goes, there you should have a transverse. Now, providing transverse becoming difficult. So, that concept of cant beams, that means these beams are somewhat radial in nature, they are referred to as cant beams. Right. So, that problem of now, so what we came from? We came from 610 millimeter frame spacing. So, the spacing of cant beam, you see, it does not follow neither 800 nor 700 nor 600. It is following, as I said, it is starting at a frame spacing of here, well, it would be 700 or 800, right? And then it is radially going out. So, that is not creating any problem. So, here 610 is for primarily for the transverse members, whatever is coming. What are those transverse members? They are the floors. They are the floors, you know, those plate floors. So, you will have plate floor at all places, all frame spacing to a certain extent. Right. Here we had plate floors at every 3 to 4 frame space. In between we had bracket floors. In forward, I will give at every frame position plate floor. Like I said, in engine room, at every frame position I give a plate floor, because heavy load is coming. Here heavy local load may come, right. In addition to that, so what we will have here is at every frame location you will have the plate floors. Obviously, here you do not have the concept of double bottom. In the rest part of the ship there was double bottom, right. Here I do not need a double bottom is not provided. So, what is done, because these floors can be of different heights, where the shape is going up, right. So, you have girders, simply not girders, sorry, floors with flanges on top. So, that provides for the strength, and then additional strength by way of, as I was saying, stringers. In between let us also draw some more things. Like here you generally have in the forward there can be one lower deck altogether. In the forward end, one lower deck, right. The access to this deck will be through some hatch here, through some hatch opening. This could be a hatch. This is for access hatch, not cargo hatch, because forward peak is not meant for any cargo carriage. You cannot carry any cargo by rule, right. But this can be a storage space. I can store mooring rope, right. It can be a kind of a store, this space, right. Plus what you have here is you can have another space curved out here, which is referred to as chain locker, anchor chain. This anchor will be somewhere in the side. So, when you haul up the anchor, where the chain goes, it cannot lie on the deck, isn't it? The chain has to be properly kept somewhere. You cannot just throw the chain on the deck, because this chain is not a very thin chain, it will be huge. Each link will have this diameter, those anchor chain. So, it has to be kept properly. So, this is there is a locker specially meant for that, which is referred to as chain locker. That means the chain will be anchored here, right. So, the chain is essentially anchored here, that means clamped. The end of the chain has to be clamped somewhere, isn't it? Otherwise, the whole end will go in the water. So, it is, so this space can be used as a chain locker, and then the rest part of the space, well, here if it is a deck, then naturally it has to be stiffened. So, it has its necessary normal transverse stiffening, because no more your longitudinal stiffening. It could be, well, either transverse or cant beams, right. And then I said that it should be strengthened against forces in this direction. So, you have stringer running along this, along the side shell. There would be, depending on the depth of the vessel, it will decide how many stringers. The stringers along the side shell means it is essentially, well, in this figure probably it will be easy to make out, that a stiffening member going like this, that red line, along the side shell, right. So, if we see a view, a transverse view, maybe in our previous drawing we have done, yeah. So, the stringers, let us assume this is our that I said some deck we have provided. We have the chain locker, right, and then the stringer, two stringers we have shown. It's nothing but a member like this. This is in the profile view along the length, along the side shell. That angle section is going like this. If I take a section here along this section is this one. Okay. So, stringer is coming in here in this fashion, right, and well, this is my floor. There is a section YY. So, I am drawing a section about this floor. So, this section Y means I am looking from this side, suppose. So, I see the full plate of the floor, isn't it? Well, that plate may have a opening here, lightning hole. Then what about these spaces? What happens is, depending on the requirement, etc., one can have even a centerline bulkhead, a centerline wash bulkhead. This I have drawn. That means there is a centerline bulkhead, a plate here in the center line, right. That means that will be visible. Well, this one here, the red dotted line, this is my centerline bulkhead. That means provided a centerline, by centerline bulkhead means a full plate, but obviously the plate we are keeping it, that will have its stiffeners connecting from the beams to the floors, because
so sir, this will be a longitudinal member.
It's a longitudinal member. It's a longitudinal member, and then you have in this those, well, in the same fashion, those big openings to keep it in a lighter condition, as well as right. This is a longitudinal member here. This one is a centerline bulkhead. It is also referred to as wash bulkhead, because this bulkhead is not the one we have talked about, transverse subdivision bulkhead. It is not subdividing the vessel, neither it is subdividing the forward peak in port and starboard tanks. It is just a strengthening member, a member in the center line. So, it is called centerline bulkhead. I may or may not give it. It is the designer's option. If your whole idea is I have to make the forward end strong, how do I do it? So, what we can see, to make the forward end strong, what we have put is that all these structural members we have taken recourse to. What we have taken? Well, in the deck, the cant beams, right, or transverse beams, it can be or transverse beams, here we have shown the example of cant beams. Cant beam is somewhere in between longitudinal and transverse, is going radially. Then second, what we are doing? Well, by providing another lower deck that adds to the strength. The lower deck also provides some strength. So there can be a lower deck, and it's worthwhile to provide a lower deck, because then I carve out some space for carriage of some items, not cargo. One of the items are the mooring ropes. You know, mooring rope means when the ship is parked in the harbor, you have to physically tie it with the shore bollards. So where do you keep the rope? You have to keep somewhere. So this store, okay. So lower deck, when you talk about lower deck, it has its own stiffeners, has to be. Then 3, additional side, this shell stiffening is the stringers. Stringer we have seen. Stringers are nothing but in the horizontal plane, stiffeners in the horizontal plane, right? Right, in the water plane, in the plane of the water planes, right? Then we have seen floors in the same concept as that of we had elsewhere in the double bottom, in the same concept, the floors. There we had the center girder, it came up to the forepeak bulkhead, then we have stopped the center girder, because here the shell is going up, the bottom shell is going up. So taking the center girder is not possible. Instead of only center girder of depth of equal to that of double bottom, I am providing a full height wash bulkhead. It's nothing but as if the center girder is going and is becoming the full height. What is the full height? Well, from the floor to the lower deck, right? So I am providing a one wash bulkhead, and that I am providing at the center line. So it can be referred to as centerline wash bulkhead. Obviously, when I am putting the wash bulkhead, it itself has to be strengthened, so it has its stiffeners. So thereby, with all these, I see you have made it quite strong. In addition to that, I can have again smaller stiffener like this in between the stringers. You see, there's smaller one. What are those? Those are actually, if you take a section of the forward bow, a water plane section, forward bow, you will find the section is somewhat like this. Oh, this is not come well. Anyway, take this line. I mean, this is my central line, right? So part of the bow is like this. How do I make the bow? Is a plate bent in this shape, right? A plate bent in this shape, and then from there it is further plates are welded, and you get the rest part. So here you provide additional stiffener. These are the ones I have shown, these small, a small plate with a flange. That is this. This is a small plate welded to the bow. That the bow plate only in the where it has been bent. The entire bow plate is coming right from here, right? This whole plate, but I am stiffening only a small part. How small it should be or how big it should be, okay, that's a matter of so-called design. So these stiffeners, they are in addition. You see, all this again in addition to that, because this forward nose, that is the nose of the ship, that will hit maximum. So it needs to be stiffened. They are referred to as breast hooks. That is how the name. Breast hooks, they are referred to as breast hooks. So, well, so that is what is the little elaborate sort of construction arrangement for the forward end. The whole idea is to make it more strong, locally more strong by floors, by stringers, by breast hooks, centerline bulkhead, right, and then well the deck beams or cant beams. Okay.